Allah, our class is going to continue the design of parallel programs, or designing parallel programs, which is the last topic in our course. So please give me a moment to open the slides. So my computer was very slow. I don't know what happened because long time I didn't shut down or restart. Okay, so guys, if you remember last week in our last class, I have discussed with you the designing of parallel programs. So we have gone through the automatic and manual parallelization. So I explained that there is a way to make the programs parallel automatically by using some tools, some parallelizing tools or parallelization tools, which is available in the market. But there are some complexity or some drawbacks or errors that could happen when we use the automatic parallelization tools. So at final, we decided that the manual parallelization is better solution than the automatic. But if, let's say, the conclusion of this topic, so the manual parallelization is much better than automatic, because in manual parallelization, the programmer will decide what parts need to be run in parallel. But in the automatic mode, so the parallelization tool will try to find some parts that could work in parallel, which is not always the best solution or the best way to make it parallel. So the automatic solution could introduce some overhead, some extra overhead, and compared to the manual parallelization will need the programmer to take care of all of the things that need to be run in parallel. So the programmer will be responsible for everything, but in the automatic, the tool is actually responsible to find the parts that could run concurrently. Okay. So if, let's say, we have a program that need to be accelerated. So we have two ways. So the first scenario, or two scenarios. The first scenario, if we have the team, or if we have human resources that should be able to make the program parallel, and also we have the budget, then it's better to make the parallel or the manual parallelization by our programmers. Okay, but if, let's say, we don't have budget, or we don't have time to do so, or also sometimes we don't have enough programmers, or even sometimes we don't have programmers at all, so in this case we better try to use the automatic parallelization tool to make things faster, and we try whether it's worthy to use that automatic tool or not. So if, let's say, we try the automatic parallelization tool, then we found that the execution time is still long, or maybe getting worse or something like that, then it's better to keep it sequential as it is, or we make it parallel manually. So here, a parallelizing compiler generally works in two different ways. So here, for the parallelizing compiler, we can use fully automatic. So in this case, the analyzer will find the parts that could work in parallel, like loops, do, for, or something like that. And the other mode is which is called the programmer directed. So in this case, the programmer should use some compiler directives to mention where is the parts that could run in parallel. Okay, so in this case, in the automatic scenario, the programmer doesn't need to care about how to create the threads, how to manage threads, and everything. He need only to use the compiler directives to mention where is the functions that could run in parallel. That's all. So so in this case, it's fully automatic. In this case, it's semi-automatic. Semi-automatic. It's not fully automatic. But this way is also not manual. This way is not considered manual, because the manual case or the manual way is to take care of all threads, and the programmer need to manage the threads, you need to manage the memory, need to manage the synchronization, need to manage the communication, and everything by himself or herself. Okay. I'm not going to go through everything. I just wanted to recap quickly to let you remember what we have taken in the last week. So here, what we have understand. Okay, so here in this steps or in this agenda, we had the automatic and manual parallelization. Then after that, the first step to understand or towards designing parallel programs. So the first step is to decide here whether to use manual or automatic. This is the first step. Depends on the human power that we have, depends on the budget that we have, depends on the time that's available for us to finish the task. Okay, so it depends on these three main things. We have to decide whether to go automatically or manually. Then the second scenario or the second step, we have to understand the problem and the program. Okay, so we have to understand the nature of the problem. So if from the beginning, if the problem is sequential by its nature, so we shouldn't think to make it parallelized. Okay, because that's really worthless. Okay, that's really worthless. It's going to waste our time, it's going to waste our resources, it's going to waste our money. Okay, then at the end, after we finish, after we waste all of that resources and money, we will run the program, then we will be shocked. Why? Because the parallel program that's trying to solve a sequential problem actually is going to waste more time than programmers that runs in sequential. Why? Because the parallel program will introduce a lot of overhead. It will introduce a synchronization overhead, communication overhead, memory management overhead, many other things. Okay. So when we add those overheads to the solution of a sequential problem by nature, it's going to be worse than the sequential program. Is that clear, guys?
Yes, doctor.
Okay. So the first step in here in understanding the problem and the program, we need to make sure that the problem is parallelizable. Parallelizable. So parallelizable means can be parallelized, can be solved in parallel. If the problem cannot be solved in parallel by its nature, then we should stop here. Don't go forward. So directly we stop here. We tell our team that the problem is sequential, then we have to solve it in sequential mode. Parallel programming is not going to work. Okay. Then, okay, what is this? And the very first step is to developing parallel software is first understand. If you are starting with a serial program, yes. If for example, we have an existing program that solves a parallelizable problem in sequential manner, then what we have to do to improve that program, the first thing is to make sure, we still need to make sure that the problem is parallelizable. If the problem is parallelizable, then the second step, we need to understand the existing code. The existing code, the existing sequential code. We need to understand it very well. We need to find where's the hotspots, where's the bottlenecks, where's the problems actually, where's the points that we can parallelize to improve or to accelerate the execution time, or to accelerate the result of the solution. Okay, so we need to understand the existing code first. Then after that, we need to, before we spend the time in attempt to develop a parallel solution for a problem, determine whether or not the problem is one that can actually be parallelized. This is actually the first thing that we have to consider. Okay, example of parallelizable problems. Here we have taken the examples here. Then I told you that this example actually is not clear for you. That's why I took the example of matrix items. So maybe, if, for example, if let's say we want to multiply some matrices, then in this case the problem is parallelizable. It can be solved in parallel or by parallel program. Okay. Because why this problem is parallelizable? Because the items of the matrix actually are independent, and also tasks of multiplication of the columns and rows actually is independent. So we can take every row and column, we multiply them in different thread independently. So multiplication could run concurrently at the same time. Okay. Here is an example of non-parallelizable problem. Actually, the non-parallelizable problem, if you remember, I explained the Fibonacci series last week, and I told you, I explained to you how to calculate this, because this, in order to calculate this item, we need to have this 2 first. And also, in order to calculate this, we have to need this 2. Also, in order to calculate this, we have to have this 2 first. So all the tasks here are dependent on each other. That's why we cannot solve this issue, or we cannot calculate the Fibonacci series in parallel mode. That's why this problem is not parallelizable or non-parallelizable. Okay, that's why don't waste your time to make this problem parallel. Okay, or to solve this problem in parallel mode. Just keep it as a sequential program. Okay. In order to understand actually the program, or the existing program, or the existing code, you need to find the program's hotspot. Hotspots means to know where most of the real work is being done. You need to understand or to find where is the main functions that have or that run the most of the work. Okay, so you need to find where is the heart of the program. Where is the main functions, or where is the heavy functions that do a lot of work, that wastes time, that takes a lot of the resources. Yeah, you need to find all of them at first. Okay, so you list them on side paper. You list all of the hotspots or the main functions that you need to work on later. Then the majority of scientific and technical programs usually accomplish most of their work in a few places. So I give you last week, I give you some example by code. So we have some functions that's very small actually, and one function which is very big. Then I asked you which one we need to work on, and we decided to work on the heavy function that wastes a lot of resources and a lot of time, right? So here, profilers also and performance analysis tools can help here. So in order to understand this thing, actually, there are a lot of tools to let you understand existing codes. One of the most common tool, actually, guys, this is very, very important thing. Please, guys, don't miss this opportunity. Side tools, understand. So this is one of the applications or the tools that's very amazing, actually, very very nice tool. I don't know how to say really. It's excellent. It's more than excellent. This tool actually helps to analyze the any existing code. If, for example, you have an existing code and you want to understand it, so maybe that code is written by other people, other programmer or something like that. So what you need to do is to analyze that code first, then after that understand it. If you want to make that manually, then it will waste your time. So try time options. Is it this one? I think it's a little bit different. Download, I'm not sure whether it's. I feel like the website is somehow different. I don't know. This tool actually is very important. You can use this tool to open an existing project. Then it can graphically show you the control flow diagrams of the application, and also yes, take control of your code. We put you in the drive seat with powerful code visualization. Oh, it seems that they add a lot of new features. That's why I feel like, okay, maybe I'm in the wrong place. But here, supported languages are Ada, Assembly, C, C++, C Sharp, COBOL, CSS, Fortran, HTML, Java, JavaScript, Jovel, Delphi, Pascal, PHP, and so on. Python also, TypeScript, everything, all common languages are supported by this tool. So easily you can take that tool. It's not free actually, but there is for education purpose you can use Crack, or you can use serial number or whatever to activate this. Actually, for me, when I need it for the education or learning purpose, I sometimes use some of the existing serial numbers available online. Then I enable the tool or activate the tool, and after that I can find whatever I am looking for easily. Okay, so this tool is really worthy. Okay, it's very important if you have an existing code written by somebody else, or maybe you wrote it but long time ago, then you forget how it works, then you want to understand it again, and you don't want to waste your time. So in this case, you better use the application that I just explained for you now. Okay, so there are a lot actually of profilers and performance analysis tools similar to the SI tools understand. So you can find one of them when you need and use it. Okay, focus on parallelizing the hotspots and ignore those sections of the program that account for little CPU usage. So here, what they need you to do actually is to focus on the big or the huge or the hearts or the main functions of the program that wastes a lot of resources and takes a lot of the CPU usage. Okay, and also they need you to ignore all sections or program parts that accounts for little CPU usage. So the functions that are very small or doesn't take long time to execute, just forget about them. Don't waste your time to create threads for them or to make them running in parallel. Okay, unless it's necessary to run in parallel. So if that sometimes a little function or small functions by itself is very little, it doesn't take a lot of resources, but because other parallel or other concurrent functions need to use it in different thread, for that reason, sometimes we need to make a separated thread for that tiny or small functions. Okay, so if not necessary, just forget about it or ignore it. If necessary, to help parallelizing other functions, then you have to make it also parallel. Guys, this topic actually is very advanced, actually, very advanced. And the course actually, this course, the SKR 3202, is not an advanced course for the parallel and distributed computing, but as a computer science students, we want you to understand the concept in this stage, because I think all of you in the first year or second year, right? What year you are, guys?
Second year.
Second year. The third semester, right?
Fourth.
Fourth semester. Okay, so you are still at the half of your journey, actually. You still have about 2 years to take more advanced topics about programming, but mostly the topics that you are going to take are related to sequential. Okay, you will take object-oriented, maybe you take Java, maybe you take Python, maybe Python for data science, maybe, or Java for object-oriented or something like that. But for parallel programming, actually, it's your responsibility to learn how to make it, because there are no standards that tell you how to make the things in parallel in a perfect way. So everybody is thinking in maybe in different way, and the tools are available. You just need to understand the concepts. Then after that, you can select your way. Okay, you can do it your way. Okay, also what you need to do later is to identify bottlenecks. Bottlenecks means the places where we have a lot of congestion. So maybe the congestion or the bottleneck is the I/O operations or functions that deals with the hardware or something like that. So in this case, we have to take care about that bottlenecks and make them working in parallel to improve or to reduce the execution time, and also to improve the utilization of the resources. So here may be possible to restructure the program or use a different algorithm to reduce or eliminate unnecessary slow areas. This is one of the options that's available. Here, other consideration, identify inhibitors, try to find where's the places that makes the or that hinders the processing or the performance of the program. So where is the places that acts in a bad manner? So the places of the program that acts in a bad way, that increases the delay, for example, or increases the resource consumption, or increases the power consumption, or whatever. So you try to find them first, then after that you try to work on them to make them or to convert them to parallel pieces of code. So one common class of inhibitors is data dependence. So the functions that are dependent on data are mostly considered as inhibitors or bottlenecks. Also demonstrated by the Fibonacci sequence above. So in this case, if let's say you have a Fibonacci sequence in your program, so that the execution is considered, that operation is considered an inhibitor for your parallel program. So why? Because this function or this series actually is a non-parallelizable problem by its nature. That's why it will stay as a bottleneck in your program. So you try to handle it carefully in a good manner. Okay. Investigate other algorithms if possible. This may be the single most important consideration when designing a parallel application. This is very important. So you have to investigate all possible or available sorry guys, try to investigate other algorithms that are available or that are considered as alternatives for the algorithms that you use in your program, because what you need to do or what you need to know is to know all available options. Then you decide which one is most appropriate for your program or for your solution. Don't stick to only one thing. Then you say no, this algorithm, for example, X algorithm is better than Y, always like that. You better try to understand the X algorithm and the Y algorithm that solves the same problem. Maybe you need to run each of them and you compare the results. So maybe for some reason you find that the X algorithm that you use in your program is very badly working and is not proper for parallel program. Then the Y is much better. In this case, you have to take the Y algorithm and use it. Okay? Don't stick to an idea, or don't stick also to a certain tool, because many of you guys, many of even my friends, actually many of my friends, they stick to a certain tool, for example Java or C Sharp or MySQL or Oracle, and they start fighting. This guy say Oracle is better than MySQL. That guy say no, MySQL is much better. MySQL is easy to install. Oracle is very bad. Blah blah blah. Like this. There is actually no point to do so. Don't stick to any tool. You have to stick to the tool that makes your life easier. So if let's say now, for myself now, I'm using actually Visual Studio. Why? Because Microsoft makes my life easier. It provides me very advanced tools, very easy to do, very easy to write a clean code. All tools are integrated in one environment. That's why I'm using Visual Studio. I know C Sharp, I know C++, I know C, I know Python, I know Java, I know many languages I can use. But I don't use Java. Why? Because the tools available for Java are not compared in terms of integration, are not compared to what Microsoft provides in Visual Studio. That's why I picked the Visual Studio. But for example, if let's say tomorrow Java makes a very good tool or very good environment, better than Visual Studio, and integrated all the needed tools inside it, directly I will move to that. I don't care. I don't care about Microsoft. I don't care about Oracle. I don't care about any company, because I care of myself only. I care about the things that makes my life easier, increases my productivity, saves my time, makes my code clean, easy to maintain, fast, and so on. Okay? So, sorry, this is not main point of this slide, but because we came to this point, actually, that's why I wanted to explain it. Because many of you and many of my friends as well, they stick to certain tool or certain technology and they fight for it. Then you fight, you sometimes lose your friends, sometimes you lose some support because you love or support some technology. Okay, that's why don't support, because the big companies are not waiting for your support. Actually, they are not standing only for your support. So if you support or not support, that's not a big issue for them. Okay, they already make their profit. Some stupid, sorry to say stupid, but some stupid people, they lose their jobs. They lose their jobs because they got opportunity to work as a programmer on a Java technology project. And they say, no, I don't like Java. C Sharp is much better. That's why I'm not going to go for this job because it's in Java. I don't like Java, and Java is very bad technology or something like that. This is really stupid, guys, because don't waste opportunities because of your support to a certain technology or a certain tool, especially at the beginning of your journey, guys. So at the beginning of your journey, you try to find the good opportunity And even if they use different technology or different tool that you never heard of, or maybe you don't like or something like that, but the salary is good and the opportunity is very good because the company that offers that job is also is a very big name, for example, that will provide you like training or some opportunities that you will never be in unless you take this job. So please, if this is the case, please don't waste that opportunity. Try to go for it. Try to learn the new technology that they use in their company or in their project. Don't reject any opportunity. I remember in 2004, I was hired as a program architect for the what they call it GCOL, General Company of Electricity Libya. So they hire me, and their existing systems was using Oracle that I don't like, because at that time Oracle Oracle database was a very heavy program, and also in order to install, sometimes you waste like 1 or 2 days to install it on a server, and it need a lot of resources. So you have to find a very heavy computer or server to install that Oracle database. So when they hire me, I don't like Oracle. I don't want to use it. Why? Because it's going to waste a lot of time, a lot of resources, but the company is going to pay me very good salary, because at that time the salary that they pay me is about 550 US dollar. At that time, it was very, very, very good salary, very high salary. Nobody was taking that salary at that time. So I directly accepted. I directly accepted and I moved. I learned Oracle. I worked on Oracle. I built a lot of programs based on Oracle technology. Okay? Why? Because I want to save my opportunity. I want to get good job, because I got supported by the company. The company pays good allowances, pay good salary. They develop us actually by training, and they give us Oracle course from Oracle company, and also they offer us many Microsoft courses and many other courses actually that supports us and improves our skills. Okay, guys, that's more than enough actually talking about the stories, but this is very important for you guys because you are now at the middle of your study. Then after that, you have to find your at least first or initial job after you graduate. And also this can be applied on the internship, guys. For the internship also, you try to find good opportunity, even though the tools or the technology that they use is something that you have no idea about. Okay, but try to learn, try to read, try to improve yourself before you start with the company, because it's very shameful for computer scientists to stand in front of something that's in the middle of the field and you say, I don't know anything about it. It's really shameful. Okay, so try to be self-learning, try to be a very good person who can develop own self and so on. Okay. Okay, guys. The last topic that we talked about last week is the partitioning. So partitioning is actually to make from the very basic angle of view. Partitioning is a very simple process that's only used to split or to break down the program or the problem into discrete chunks or discrete parts of functions or parts of data or whatever. So the thing is to break down the problem or the program into discrete subparts or sub chunks. Okay, so here the partitioning actually is also known as a decomposition. It's the same meaning. So decomposition has two ways. Actually, the first way is the domain decomposition. The second way is functional decomposition. Domain decomposition is based on the domain, and functional decomposition is based on functions. So if you remember last week, guys, I'm doing this recap because this is very important, guys, for you for the test 2 and also for the final exam, because this topic has some questions in the final and some questions in the test 2. Okay, so here, if you remember last week, we have taken the example of salary calculation, university staff salary calculation. So as I said, if we want to make it break the problem into discrete chunks based on domain, then in this case, we can divide the staffs, the people of the university into 2 or 3 groups, for example. So the first group may be the academic, the second group is non-academic, for example. Then we take two concurrent functions, or to run two concurrent functions to calculate the salary for the two groups at the same time. So every function is responsible for its group. Okay, or every thread actually is responsible for a certain group, but the two groups are using the same function, guys. So in this case, they call it domain decomposition. But if, let's say, we want to break the problem based on functional decomposition, so in this case, we can keep all stuff together as one group. So here there's no domain decomposition, but after that we make the calculation, or break down the calculation function into small functions. So maybe the first function that calculates the tax, the second function calculates the what they call it, the allowances, and maybe the third function is to combine the things together and calculate the final salary. So in this case, this separation is called functional decomposition. Functional decomposition. Why? Because we decompose the program based on the functions. Okay? And also, we can have something called hybrid decomposition. So the hybrid decomposition, it could be a mix between domain and functional decompositions. Okay? So maybe we divide the people or staff of the university into two groups, academic and non-academic staff. Then after that, we decompose the program into multiple functions. So we have the tax function, what they call it. The other function is the allowances function, and so on. Then we take the data and we give it to many instances for the tax function, and run it at the same time. Okay, guys. So I already explained this last week, but maybe what we need to do is to make it again. So if, let's say, this is the stuff, okay? The group of stuff. Okay, this is non-academic, and this is, for example, academic staff, and this is non-academic staff. Okay, so if, let's say, the function is called calculate salary, like that, and here we give it staff, we pass a staff info, staff data, to the function to get the salary. So in this case, we have to have this function, for example, in a for loop for each, for example, for each staff. Oops. For each staff like that. For each staff, we calculate the salary. Okay, so in this case, what we need to do actually is to calculate all staff members here in this loop, right? One after another. So this thing actually is a sequential program. What if we want to calculate, if let's say we have a function, that be called calculate salary, like that, then this function takes staff data, and this function is makes the calculation. Okay, so this function actually is not designed for academic or non-academic. It can handle both of them, right? So we just give the data, then the salary will be calculated. Okay, I want to leave a room here to add some other code later. Okay, so what if we make two copies, two instances of this function? So if we want to make it serial, then we use for loop, and we call this function, and we pass the data one after another. Then we calculate sequentially for all stuff all together. But if let's say we want to calculate for the NAS, the non-academic, and in a different thread, and the academic in different thread. So in this case, we have to take one copy. We call it for each NAS like that. Then we calculate salary, the same function, calculate salary. I just want to use the same name exactly. NAS. Okay. For each NAS calculate salary as data, then in, for example, I don't want to make it exactly as the exact code, but I want to just give you like pseudocode to understand how it works. So here we create a thread for the calculation of NAS data, and then we take another or maybe better remove this. So maybe we need to create one thread for the NAS data and another thread maybe thread 1 here, and this is thread 2 to calculate the what they call it, AS data. So in this case, what we have to do is to have another instance of the function, right? So we have the same function here, but this function is calculated or copied into two instances, and every instance is given to a single or independent thread to be run in concurrent or in parallel mode. Okay, in this case, the separation or the decomposition is called here domain. Why? Because we separate or we break down the application into the two chunks based on the data, based on the domain here. So one domain is for non-academic and the second domain is for academic stuff. So the calculation for non-academic is run in trade number 1, and the calculation of the salary for the academic staff is calculated in trade number 2. So these two trades are based on one function, Okay, this is the domain based. Okay, let us see what if, for example, we have like calc tax stuff data and calc allowance stuff data. Okay, like that. So what will happen here? Let me change this to cover that text. Okay. What if we have these two functions and these two functions are independent? So the tax calculation is really or fully independent of the allowances calculation. So in this case, we can separate or decompose the program into different functions, right? So in this case, if let's say we make only one thread, or maybe we make a for loop like that, for loop, and we say for all stuff, no differentiation between the academic and non-academic, and we say for example thread 1 is calc tax stuff data, and the other thread is like that, calc allowance stuff data. So in this case, we make different threads for different functions actually. So every thread is running different function, not like the previous example where the thread 1 and 2 they run two instances or two copies of the same function. This scenario here, the two threads, each thread runs different function. So this is what they call it functional decomposition. And here we do so, we calculate the tax independently for all stuff. We don't separate them as a non-academic or academic. We don't split them. We don't break them into two domains. Okay? So in this case, this is what they call it functional decomposition. But also we can make it hybrid. So we can say here, this is for NAS, and we can have also another thing for academic stuff. So here, this we can say academic stuff. This also we can say academic staff data, and this one is non-academic staff data. This one is non-academic staff data. So in this case, the scenario actually, or the decomposition is a hybrid decomposition. Why? Because it decomposes the entire problem based on the domain or based on the data into two groups, which is non-academic and academic groups, and each group will do its own calculation in different trade. Okay. Then after that, inside each trade, for example, the non-academic staff, we have multiple trades for each function. So the first trade will be to calculate tax. The second trade will be to calculate allowances. So this is how how we can make a hybrid decomposition solution for a complex scenario. Okay, is that clear, guys?
Yes.
Any question?
Yes, Doctor.
Any question in this regard? Okay.
No question, Doctor.
Okay. That's all about this, guys. I'm not going to go through all of that stuff, that funny stuff, because they use colors here to explain to you how this can be partitioned and so on. But for my case, I prefer to use real examples or real scenarios that instead of these colors, because as you are still juniors in the computer science, so I cannot rely on colors, because colors sometimes some of you cannot understand what is the meaning of this color. So how in the real life a color could be, or what it could mean in the real life. That's why, okay? So just always remember the scenarios that I explained last week and this week in order to understand how it could work. So here we have functional decomposition examples, like or scenarios like in ecosystem modeling, signal processing, climate modeling. I already explained this last week. Actually, it's a general example. So, for example, for signal processing, the process could be chunked, actually, or could be decomposed to into multiple groups. So we sorry, guys. We take the entire signal length, then we chunk it or split it into multiple subparts of the signal. Then we give them to the process 1, process 2, process 3, process 4, which means which represent some filters as per the example here. So every signal actually have to go through all of that 4 filters. So we cannot make these filters parallel. Why? Because its nature is sequential. So the result of the process or the filter number 1 is input for the filter number 2, and the result of filter number 2 is an input for filter number 3. So that's why we cannot make a functional decomposition here, but we can also run it in parallel by breaking the data or the signal into multiple subparts of signal. Then we can run that filters based on the subparts of the signal. Then after that, we can combine them together to get the final result. Okay. Now we have the new topic or subtopic is the communication. We stopped here last week. Okay, guys, when we talk about parallelizing things or solving problems in parallel, we have to think about many things. The first thing, or first and important thing, is this communication and synchronization. Communication and synchronization. Then after that, after we think about this and we solve these things, we consider them, then we will have other things that will be introduced after that, which is the data dependencies, load balances, granularity, I/O, many other things. I already explained this in our previous classes in many ways, especially the granularity, the load balance, and so on. But we still have to go through in more details. Okay. Who needs communications? Guys, can you answer this question? Not in general, guys. Huh? Who needs the communication, or what we need this communication for under the umbrella of this topic? Anyone has an answer?
To do certain task.
Yes, definitely is to do certain tasks, but why we need communication? Okay, the question in different way. I will ask you the same question, but in different way. For sequential programs, guys, do we need communication inside the program itself?
No.
No, right?
Yes. No.
Even though we still need a little bit of kind of communication like memory sharing or something like that, but we cannot say that communication. That is a communication, okay? So in sequential programs, we don't rely on communication. We rely only on what they call it, memory sharing between the tasks, but the tasks, because the tasks are running in sequential mode, so we have only one task running per time. So that's why we don't have problems of communication, we don't have problems of synchronizations and so on, okay? But for parallel programs, the issue or the thing that's introduced by the parallel new thing is that there are multiple instructions or multiple functions are running at the same time, and those functions could need to share some information or could need to exchange some information or data between them. That's why who needs the communication here in parallel programming? Actually, the tasks or the threads. So every thread, sometimes some threads are very fully independent from each other. That's why they don't want to communicate. But in some scenarios, they are somehow related or somehow dependent or semi-dependent or fully dependent on each other or something like that. So in those cases, they need to do communication and also they need to do synchronization. Whenever we require communication, the synchronization is going to be very necessary, very important to be done. Otherwise, if we have communication but we don't have synchronization, then mostly results will not be correct. The outputs of your program will not be correct. Okay, so let us go through the slide. The need for communications between tasks depends upon your problem. Guys, in what week we are? Is it week 11 or 12?
Now is week 10.
Oh, week 10. So we still have 4 weeks. Okay, good enough. Okay, so here, you don't need communications. Some type of programs can be decomposed and executed in parallel with virtually no need for tasks to share data. Why? Because those concurrent tasks or parallel tasks does not need to exchange data among themselves. Why? Because each task is fully independent from others. Okay, for example, imagine an image processing operation where every pixel in a block and white image, in a black and white image needs to have its color reversed. Okay, so suppose that we have black and white color, black and white image need to do some processing to reflect or to reverse the colors of all pixels in the image. So in this case, each pixel actually is fully independent from others. So what we need to do is to take pixels pixel by pixel, and if the pixel is white, we make it black. If it's black, we make it white. Okay. Do we still need to exchange data from about the other pixels? Do we need to know data about other pixels? Definitely no, right? So the image data can easily be distributed to multiple tasks that then act independently for each other to do their portion of the work. Okay, suppose that this is the picture. Suppose that this is the picture, like this, or the image, black and white image. Then suppose that we have to reverse the colors. So the white, we make it black, and the black, we change it to white. So maybe what we need to do is to split the image into multiple parts like that. Okay. Then we assign the data to multiple threads. So maybe this one is thread number 1. This one is, for example, thread number 2 is responsible for this area. Then maybe thread number 3 is responsible for this area, and until thread n. Thread n. Okay, so the thread number 1 here is responsible only for this, to reverse the colors of pixels in this area only. Is it still need to exchange some data with thread number 2? Does it need to know about the pixels available in the area of thread number 2? Definitely no, right? So here the tasks are fully independent. Tasks are fully independent. Is that clear, guys?
Yes, doctor.
Yes. One more thing, because we came to this point here. We came to this point here. Let us take the opportunity. Actually, dividing this image into multiple parts, as you can see here, n parts, right? So those n parts are 16, right? So n is equal to 16. So here, the n actually is representing the granularity of the program now. Because if you split or if you increase the n and make it like 100, so in this program we will have 100 threads, and every thread is responsible for a very small size or very small area of the picture, right? So this is, in this case, if for example n is equal to 100, so in this case we maybe call it fine granular, or this program is running in fine granularity. Okay, is this spelling correct? Granularity. Okay. Okay, granular. This is called fine granular. Okay, or this is fine granularity. Okay, but if let's say n is equal to 2, this is what they call it, coarse granular. Coarse, oops. coarse granular. Like that. I'm not sure about the spelling. Yes, correct. So this is called coarse granularity, and that one called fine granularity. What does it mean? Fine means fine. Coarse means coarse. You know what is the meaning of coarse? The meaning of coarse.
Yes.
What is that in Bahasa Malay?
Kasar.
Kasar. Yes, correct. Okay. So this is called kasar. You know the sand, right? Sand. If the sand is very fine, that means every piece of that sand is very small, right? But if the sand is coarse, then every piece is a little bit big, right? So this is exactly the concept that's used for the granularity here. So some applications, when you make them, I mean, you make the granularity very, very fine, they work better. And some applications, when you make them very coarse, they run better. So here, the concept actually, fine, like that, and coarse, like this, is to, I like to elaborate the things in this way because really that makes you understand. So this is towards sequential, and this is towards okay. So if opposite way. Parallel. And this is towards sequential. So if let's say we have a program that could run in multiple threads, but we suddenly decide to make the n equals to 1. So we make the n equals to 1. So in this case, how many threads we have? If we make n equal to 1, how many threads we will have in this application?
One
thread, right?
One.
So if one thread means sequential, right? And the application in this case, the granularity is very coarse. Very coarse. That's why the program will run in sequential. But if we make the n equals to 2, so in this case, we will have two threads. Two threads, but we have a lot of data, then every thread will take very long time to finish. Okay? Then here, it will run in a program, in parallel program, but the parallelization is not enough here to save the time. So maybe it will break the time into the half. So for example, if the entire picture in sequential mode takes 100 seconds, so if we make the n equals to 2, it may take like 50 seconds to finish. Why? Because we have two threads here. Every thread will consume about 50 seconds, then together it will be finished in 50 seconds. So we will save the half of the time. What if we make the n equal to 50? So in this case, every thread will need to consume about 2 seconds. So 50 threads, and every thread is about 2 seconds. So it may take, like, if we have enough resources, it may take about 2 seconds to finish the entire picture. If we make the granularity very fine, very high, like n equals to 100 or n equals to 50. But sometimes, if let's say the picture has only 1,000, or for example, to make it easy, let the thing let's assume that the picture, let's assume that the picture has only 100 pixels, and we make the n equals to 100. So in this case, every thread will handle only 1 pixel, right? Every thread will change the color of 1 pixel. So here, the cost of creating a thread and calling it in the memory, it's very high compared to the payload or the workload. The workload is very little. So also very fine granularity sometimes is going to waste our resources. So the problem here for parallel programs is always when we need to, or for how much we need to put the granularity, or what is the perfect value for the n. What is the perfect value for the n? So in this case, what we need to do is called load balance. So what we need to do is to load balance. We need to decide what is the good partitioning that's enough to save time and not wasting the resources at the same time. So we don't want to make one thread for 1 pixel, and also we don't want to execute or to process all pixels in the picture in one thread. Okay, guys? So 1 pixel in 1 thread is not a good idea, which is very fine granularity. It's not a good idea because the cost of creating the thread is higher than the cost of calculating or processing 1 pixel. And also, processing the entire pixels in the entire picture in one thread is actually time consuming. Why? Because the workload is very high or very heavy to only one thread. So what we need to do is to decide what kind of we need to decide what size we need to use for partitioning. Okay, guys, we have another example. We have another example that's much easy to understand. Suppose that that we have like mine, you know, mining area. So suppose that we have very big, very huge stones here that need to be taken from the mining area to the factory, for example. Okay. This one, huge stone. Rocks. Okay, huge rocks need to be transported to the factory. So here, what they have to use, actually, they have to have trucks like that, trucks like this, then like this. Okay, and they have to put one stone or many stones. So if, let's say, we take all of that stones here and we put it here in one truck, what will happen? Suppose that we need to take all the rocks at once using one truck to the factory. What will happen here? Guys,
The process is very slow.
The process is very slow, but also we need to have very huge truck, right?
True.
Yes, very huge truck. What does it mean for us here as a computer scientist? It means very huge machine, right? Or the machine that has very huge resources. Maybe the memory is supposed to be like 32 gigabyte or something like that. Maybe we need to have like a very fast processor, single machine processor, but the frequency of the processor must be like 10,000 gigahertz, for example. to handle all of that stuff, all of that process. Okay. Also the time, because this thing actually is going to be very heavy, then it will require a special road. Why? Because the truck is very huge, then the huge truck cannot go very fast, the speed will be very slow, so it will take time. Maybe the speed of the truck will be like 5 kilometers per hour, so it may need like 1 or 2 days to arrive at the factory. Okay, so in this case we wasted time, we spend a lot of money to build this special machine or this special truck, and also we spend a lot of money to make the special conditions of the road from the mining area to the factory. So that's all resources, right? Okay, and also the time is going to be very slow to deliver the things to the factory. So what if we take this like that, and we send them one rock after another, and each rock is in different truck. Okay, so what will happen here? What will happen here? Maybe small truck cost is less than the huge truck cost. So here we will save time, right? And instead of making a single processor very fast, that which will cost a lot of money, we try to make maybe multiple pieces of hardware that could handle the small pieces of data or workload. But here we still have to run the things sequentially. Why? Because this truck number 3 here cannot arrive to the factory until the truck number 1 deliver. Then after that, the truck number 2 must deliver first. Then after that, truck number 3 will be able to deliver. So in this case, the thing is sequential. Okay, still sequential. But here we still we saved a little of the money or the cost. Okay, and the time because every truck is responsible to handle a small piece of rocks, so it could run very fast. So maybe instead of 5 kilometers per hour, it could run like 90 kilometers per hour. So the delivery time will be less. Delivery time will be less. Okay, what does it mean here in computer science? This way is a very good memory and resource management. So this is how to will manage the resources that you have in the machine. So instead of uploading all data at once into the memory, then you start handling them at once, which will need a lot of resources, like a very huge memory, very huge or very fast and super processor, which is very high costly, and so on. So in this case, instead of uploading entire or the entire data together at the same time into the memory, we try to take the data chunk by chunk, upload it to the memory, run it first. After it finished, we take the other part, we compute it, and until we finish. Okay, so this is a part of the solution. Okay, guys. The other solution is to make them like that. Okay, so instead of sending traffics or sending trucks or lorries one after another, so we send the trucks by batch. So maybe we can send like 10 trucks at the same time. 10 trucks at the same time. What does it mean? Okay, guys, we missed something actually. We missed something here. In this case of the sequential, why we make it sequential? Sometimes because of the nature of the rocks. Maybe rocks here has or the workload maybe has by its nature is ordered. Or sorted based on some criteria. So in this case, we cannot process the truck number 2 before truck number 1. So if this is the nature of the program, so we cannot do anything. We have to be sequential. Okay, and sometimes also we have only one pipeline here, one pipeline, okay, or one assembly line, for example. So here, if let's say we have only one machine that could take the rock and put it in a truck, so in this case, what we have to do is to send trucks one by one. Why? Because here we have only one truck that could one bulldozer, for example, to handle the rocks and pick them and put them inside the truck. Okay, what if we delete this? What if we have multiple bulldozers? So here, if let's say we have 2-3 bulldozers, so what we can do here is to handle 3 trucks at the same time. So those 3 trucks could go at the same time in the same speed and deliver their payload to the factory, right? So here what we have like 3 processors or 3 tasks at the same time, right? So they can reach to the destination at the same time. So here the granularity, actually the n is equal to the number of stones here, and the batch is equal to 3, and the 3 here is based on the resources. So always the granularity depends on, we have to consider the granularity or to calculate to set the n of the granularity based on what we have of the resources. How many processors, how size of the RAM, and everything. So it's not only you make n equal to 100 or 1000 and that's all, and you have only dual core processor. So in this case, there is no point. Maybe you would introduce extra overhead, then the result will be worse. Okay, so this is how it works. So the much you have is the better. So suppose that the rockets here are very huge. Maybe we have like billion rocket in the site here. So is it worthy to buy extra trucks and extra bulldozers? Definitely yes, right? Because buying the bulldozer, maybe the bulldozer is like $50,000 US, for example, and the truck is $20,000 US. But because here we have billion rocks, so if we don't buy new bulldozer and new truck, maybe we need to spend more than our life, and we cannot finish that number of rocks. So in that case, investing money in buying extra bulldozers and trucks is a very good idea. It's feasible. Okay, so that's why we need to buy extra bulldozers and extra trucks. And whenever we increase the number of bulldozers and the number of trucks, the process and the operation is going to be improved. But this, we have to make sure that this number of trucks and this number of bulldozers should not exceed the capacity of the factory, which is also considered as resources. Okay, so otherwise, if we make a lot of trucks and a lot of bulldozers, then here will be a lot of congestion in front of the factory, and maybe the trucks cannot move anymore and cannot deliver their stones or their rocks anymore to the factory. So we have to consider all of that stuff. Okay, one more thing, which is also very important. What if, let's say, we have only 100 rocks, only 100 rocks, and we need to deliver that rocks to the factory? Is it feasible? Is it worthy to buy many bulldozers and many trucks for that 100 rocks only? Definitely no, right? Because after we finish that 100 rocks, then this resources actually is going to be put aside, and there will not be utilized. This is exactly as if we increase the number of processors in our machine for only one program that runs only one time in a year. So in this case, the resources actually will be very costly. Then it will be rarely used, and this is going to waste our money and our resources. So that's why we need always to be wise and to think carefully about when we need to increase the number of resources or the number of processors or the size of the memory. Depends on what we have or depends on the workload. Okay. So in the case of 100 rocks, it's better to have only one bulldozer and one truck. Maybe if the truck takes about 1 day, then maybe 100 days, all the rocks will be delivered to the factory. But if, let's say, this 100 rocks must be delivered to the factory into like 30 days, necessarily, we have no choice. This is the requirement of the organization, that 100 rocks must be delivered in 30 days. And every truck needs 1 day for the round trip to go from the site to the factory and back to the site. So in this case, 100 by 30 is equal. So we have 100 rocks divided by 30 days, which is the maximum time that we have to consider. So in this case, it will be equal to maybe 3.3, right? 3.3. So what does it mean? This means we have to have 3.3 trucks and 3.3 bulldozers. So what if, can we have 0.3 bulldozer and 0.3 truck? Definitely no, right? So what if we try to make 3 bulldozers and 3 trucks? So in this case, in 30 days, every bulldozer and truck will deliver 30 rocks. So it will deliver in 30 days 90 rocks in total, right? And this is below the requirements of the organization, so it doesn't work. So what we can do in this case, we have to make this 4, because we cannot have 3.5 processors. We cannot have 3.5 processors. We can have either 3 or 4 processors. So in this case, we have to make it 4 processors, which is more resources than we exactly need for the requirements. But this is the minimum resources that we could use to handle that requirements. Okay, guys? So in this case, the capacity or the capacity of our resources is to deliver 120 rocks per 30 in 30 days. Okay, so definitely the work will finish before 30 days. Okay, this is how we need to calculate the resources, and when we need to increase the number of processors, when we need to increase the size of the memory, and how to consider the requirements of the organization. Okay, guys? Is that clear?
Okay, Doctor.
Guys, honestly tell me, is it clear or not?
Yes, clear.
Clearer.
Okay, good. Okay. One more thing, guys. In this scenario, uh, because the rocks are really independent, fully independent, so we don't have to have communication between the trucks and the bulldozers, right? So that truck, once the bulldozer is ready to pick a rock and put it in the truck, they have to do it as fast as they can, right? They don't need to care about other bulldozers. They don't need to care about other trucks and so on. Okay, that's why they don't need to have any communication between them. Okay, but if let's say, for example, because we have a limited resources, for example, so maybe we have one bulldozer for two trucks. One bulldozer for two trucks, like this. This is one bulldozer, this is one truck. One bulldozer, two trucks. Okay? So in this case, these two trucks need to have a kind of communication. For example, the truck number two, for example, this is 1, 2, 3, 4. So maybe, for example, if the truck number one enters the site and the bulldozer pick the rock and put it in the truck, then after that, maybe the truck driver, the truck number one driver, maybe need to communicate with the truck number two driver and ask him to enter the site after the truck number one driver leave, for example. Okay, so in this case, they need to have kind of communication. Why? Because they have a shared resource here between them. Okay, this bulldozer actually is shared between the two trucks, and also this bulldozer is shared between these two trucks. That's why the two trucks need to be communicating between each other, or maybe between them, among them and the truck driver, and so on. Depends on the requirements and depends on the nature of the problem. Okay, guys? So this is when we need to have communication. And also, whenever we have communication and shared resources, then we have to have synchronization, right? So we have to synchronize. If let's say the two trucks, truck number one and truck number two, arrives at the site at the same time, then there's supposed to be some thing or some or a person or machine or a processor or task or whatever or thread that should be responsible to arrange which truck supposed to be go first. Okay, so suppose that the two trucks came to the site at the same time, then somebody need to tell the truck drivers which one need to go first to the bulldozer to pick up the rock. So this is what they call it synchronization. Okay, this is what they call it synchronization. So if let's say the thread allows the driver number one to go and pick the rock, and decides to make the truck number two waiting for a little for a while until the truck number one finish. So this is what they call it lock and wait. Okay, so the resource here, which is the bulldozer, is locked for the driver number one or for the truck number one, and the truck number two need to wait until truck number one finished. Then after truck number one finished, it should release the bulldozer, and the bulldozer should be free to be locked by the driver number two, maybe because truck number three or truck number five is still waiting for this bulldozer. So this is how the lock and wait process could work, which is actually a technique for the synchronization purpose. Okay? Is that clear, guys?
Yes, doctor.
Okay.
Yes, doctor.
Okay, now what we have to learn here about the communication. So we here take the black and white image, and I already explained about it. The image data can easily be distributed to multiple tasks that then act independently for each other to do their portion of the work. So here, multiple processors or multiple tasks is very necessarily to be available or to be used to improve the time or the execution time of this image processing. Okay. These types of problems are often called embarrassingly parallel because they are so straightforward. Very little inter-task communication is required because here all tasks are independent, fully independent. So there's no communication requirements here. Okay. You do need to communicate, or you do need communication. Most parallel applications are not quite so simple like the first scenario, and they require tasks to share data with each other. Maybe because the data nature is like that, like Fibonacci series or something like that. So the data is dependent on each other. So item number 3 cannot be calculated until it receives the OK from item number 1 and item number 2. So they need to exchange some data to be calculated or something like that. So, and also the scenario of the bulldozers and trucks. So the truck number 2 cannot pick a stone or cannot pick a rock until truck number 1 finish because they share the same bulldozer. So here, for example, a 3D heat diffusion problem requires a task to know the temperatures calculated by the tasks that have neighboring data. You see, the scenario now is a little bit complicated. Even sometimes you cannot understanding until you read it many times. Okay, so changes to neighboring data has a direct effect on the on that task's data. So in this case, if let's say the scenario is very complicated, so maybe the pixel color must be changed to different colors, maybe black, maybe gray, maybe white, maybe yellow, maybe blue, something like that. So if for example, the pixel neighbors are black and white, then it should be gray, for example. And the neighboring pixels need to be known first. So they have to reverse their colors first. Then after that, the middle pixel can reverse its color. Depends on the neighboring pixels colors. So in this case, they have to have a kind of communication, and they have to have like look and wait technique. Okay, so look and wait technique is mostly used in most parallel programs. It depends on the nature of the problem. Everything in this field, actually in the parallel programming field, everything is based on the nature of the problem. So the techniques that you can use sometimes is limited or limited due to the nature of the problem. Okay, so maybe some techniques are proper for certain scenario, which is not proper for another scenario. Okay. Factor to consider, number 1. There are a number of important factors to consider when designing your programs, inter-task communications. So the first thing is cost of communications. So cost of communications is virtually always implies overhead. Okay, inter-task communication virtually always implies overhead, because the communication actually is also a process. It requires processing, it requires memory, it requires time, and everything. And all of that actually is money, right? So that's considered overhead. So the communication is costly. So what we need to make sure of is that the cost of the communication is not higher than the cost of calculating or processing the problem in sequential. So if for example there's a problem X that wastes like $10 to be solved in sequential, but if we make it in parallel, sorry, again, if let's say we have two arrays, for example, to multiply, and that two arrays can be multiplied in 2 hours sequentially. So if we multiply them sequentially, they need 2 hours, and that costs like $10. But what if we make it parallel, so they can finish the multiplication in half an hour, which is a quarter of the time needed per the sequential, but the cost here is 20. So the cost is still the same, right? No, the cost at the sequential is 10. So let us say that in parallel it could finish in half an hour, and the cost still the same is 10. So in this case, which one is better? Definitely to run or to solve that problem in parallel mode, because it costs the same cost, $10, but it saves the time. Okay, what if the cost is higher, for example, $20, but it saves the time to the quarter? It finishes in 30 minutes. So here we have to do balancing. So if the time is very critical, for example, we are talking about fire detection system, so the time is very, very critical. Otherwise, if let's say the system cannot detect the fire very quickly, then it may burn all of the building or something like that, and then we will lose a lot of money and the system will be useless, right? So even though the cost is higher in parallel, but it saves the money, it saves the building, it saves the critical resources, then here we have to go for it. But if let's say the problem is only multiplication of arrays, that's no problem if it's ready in 2 hours or even in 1 day. Nobody cares. So in this case, is it better to go for a parallel that costs $20 or to keep it sequentially that costs only $10? So in this case, it's better to keep it sequential, because here we have to consider our organization requirements here, or the business requirements. So here, if nobody cares what time it needs to finish, then in that case we have to better keep it in sequential to reduce the cost. Okay, what if the multiplication requires 2 hours and costs $10 if we solve it in sequential, but if we solve it in parallel, it saves the money, it executes, it costs only $5, and it wastes, or it needs only half an hour. So in this case, this is actually the heaven of a programmer, actually. So all the requirements are satisfied now. We reduce the cost, we reduce the time. So your boss or the person who hires you will be very happy if you provide this. So definitely in this case, you better go to the parallel solution. Okay, so parallel solution here is much better than the sequential. Okay. What if the worst scenario? What if the sequential costs $10 and spends 2 hours, and we make it parallel, and after we finish, we realize that it takes 3 hours and costs $15. So in this case, definitely we have to keep it sequential, because the parallel parallelizing the solution is not good at all. it's not providing any advantage. Maybe because of the nature of the problem. Okay, so in this case, we have to keep the program or to keep the solution in sequential mode. Okay. So here also machine cycles and resources that could be used for computation are instead used to package and transmit data. Okay. What does it mean? Machine cycles and the resources that could be used for computation are instead used to package and transmit data. Yes, because here, whenever we need communication, we have to keep some resources to handle the communication process, which is to package and transmit the data, and also to receive and depackage the data in the other side at the receiver. Okay, communications frequently require some type of synchronization. Yes, because whenever we have communication, then we have to apply a synchronization technique like look and wait or whatever. Okay, so it requires some type of synchronization between tasks, which can result in tasks spending time waiting instead of doing works. Okay, like the truck scenario here. If let's say truck number one looks the bulldozer, and the bulldozer try to pick the rock and put it in the truck number one, and during that time maybe the tire is flattened or something like that, or maybe the engine cannot start, or maybe the bulldozer is stuck or something like that, then the other resource, which is the truck number two, is going to be wasting its time waiting for the process number one to finish. And in this case, it could lead to something called deadlock. Okay, so that the look and wait scenarios or techniques could lead to deadlock scenario, which is a nightmare for programmers. Okay, guys? So we have to be careful whenever we have multi-threads. If we have communication, if we have look and wait, we have to be very careful, and we have to take care of avoiding the scenario of deadlock. Okay, no matter how it costs. So because deadlock is very bad scenario, and it could collapse the entire solution. Okay, so competing communication traffic can saturate the available network bandwidth, further aggravating performance problems. So here the communication actually between the process, between the tasks, need a lot of bandwidth for communication, and maybe need a lot of memory space to share the resources or to share the information or data. So in that case, maybe the resources or communication resources could be congested. Then after that, it could increase the performance problems. So if let's say we have a cluster which includes a lot of machines, and the communication actually is going to use the communication network between the machines. So in this case, if the communication network is very limited, like 10 megabit per second speed, which is not enough, so maybe the network will be congested. And sometimes we use the communication inside the same multi-processor machine based on shared memory, so the memory could be also congested or maybe overwhelmed. Okay, so that's why we have to consider all of that scenarios, and we have to always keep in mind not to overwhelm the resources that we have. Okay, factors to consider number 2. So we have the latency versus the bandwidth. So latency is the time it takes to send a minimal 0-byte message from point A to point B, commonly expressed as microsecond. So bandwidth is the amount of data that can be communicated per unit of time, commonly expressed as megabytes per second. actually this thing is megabit per second, or could be megabit per second and could be megabyte per second. Depends on if file transfer speed, they normally use megabyte. If bandwidth speed, they normally use megabit. Okay, depends on what you are measuring. So sending many small messages can cause latency to dominate communication overhead. Often it's more efficient to package small messages into a larger message, thus increasing the effective communication bandwidth. Okay, so here actually is another concept. Whenever it comes to communication, what we need to have is to have data, right? Data need to be sent. Then that data need to be packaged. So we need to attach some header, right? Then after that, maybe we need to have encapsulation like that. Then for the encapsulation in different layer, maybe we need to insert another header. Okay, so this is what they call it, communication processing overhead. Okay, so if let's say the payload here is very small, then sometimes the cost of headering and processing will be more than the cost of transferring the data. That's why the size of the messages is very important to be carefully decided. Very important. Okay, so it's not a good idea to make messages very small with bigger header, and also it's not a good idea to make the message very huge and send all the communication data at once. So there will be always a threshold for the packet size or the message size, and that threshold need to be perfectly or optimally set. Otherwise, it will introduce an unnecessary overhead of the communication. Okay, so factor number 3, visibility of communications. So with the message passing model, communication are explicit and generally quite visible and under the control of the programmer. Okay, so here the messages actually is very clear, explicitly visible, and could be controlled by the programmer. So the programmer could decide the size of the message, could decide when they need to send the message and how they send it, and so on. So with the data parallel model, communications often occur transparently to the programmer, particularly on distributed memory architecture. So the programmer may not even be able to know exactly how inter-task communications are being accomplished. So in this case, in the data parallel model, the programmer doesn't know how the communication actually is going to be done and how the inter-tasks communication are being accomplished. So that's why he cannot do much with that. Okay. Synchronization, synchronous and asynchronous communications. So synchronous communications require some type of handshaking. Yeah, they have to do kind of handshaking for the synchronization purpose between tasks that are sharing the same data. So this can be explicitly structured in code by the programmer, or it may happen at the lower level unknown to the programmer. This is the scenarios. So we have to consider what kind of communication we have. Is it asynchronous or synchronous? Then based on that, we have to pick up the proper solution or the proper technique to handle that. So synchronous communications are often referred to as blocking communication, since other work must wait until the communication have completed. This is exactly similar to the scenario of lock and wait here. Okay. So as I said, the scenario or the technique that we need to handle the memory or to share the resources depends on the nature of the application. So for the scenario of this truck and bulldozer, we can use sorry guys, we can use the technique of look and wait. So truck number 2 should wait until truck number 1 finished. Then after that, the bulldozer will be free. Then bulldozer number 2 could look the bulldozer, and the bulldozer could pick up the rock, put it in the truck, and the truck could leave and release the bulldozer to another truck, and so on. This is what they call it look and wait, or as they said here, blocking communication. The factor number 4, synchronous and asynchronous communication. Asynchronous communication allow tasks to transfer data independently from one another. For example, task 1 can prepare and send a message to task number 2, and then immediately doing other works when task 2 actually received the message does not matter. So this is what they call it asynchronous. Why? Because the time is not necessary. There is no matter what time the task 2 receives the message from task number 1. So that's why the task number 2 shouldn't wait for the message from task number 1, because whenever the message came, the task number 2 will be ready. But during that time, task number 2 is not waiting for the message from task number 1. During that time, it's doing another things. So this is what they call it asynchronous. Asynchronous communication are often referred to as non-blocking communication. Why? Because task number 2 will not be waiting for task number 1 until it finish or send a message, and vice versa. Okay, so that's why it's called non-blocking communication, since other work can be done while the communications are taking place. So interleaving computation with communication is the single greatest benefit for using asynchronous communications. I just want to finish until this. Oh, there's a lot of things actually. Okay, guys, maybe we vote. Can we finish this 4 slides? Or you want to leave? Because now is 4 and 10 p.m. Could you wait until we finish this? Are you okay, guys?
Can Doctor.
Okay, doctor.
Okay, good. I feel like there's one representative for the entire group of yours actually. We have 29 students, and only 1 or 2 students are talking. The others are I don't know what they are doing now. Anyway, the video will be uploaded to the YouTube channel, so anytime you can refer to it and you can use it as a reference. Okay, guys? Okay, let us continue with the factor number 5. So here, scope of communication. So knowing which tasks must communicate with each other is critical during the design stage of a parallel code. So we have, during the design stage, we have to know what task or which task need to communicate with the others. That's why we have to arrange and we have to prepare everything to fulfill the requirements of the communication, and we have to be in full control of that communication. And also we need to be careful to avoid the deadlock scenarios. So both of the 2 scopings described below can be implemented synchronously and asynchronously. So we have something called point-to-point communication, or that involves 2 tasks with one task acting as the sender or producer of data, and the other task is acting as the receiver and the consumer. So one task will send the data and the other task will receive and process. So in this case, they call it point to point. Okay, the other one is collective. So in this case, it involves data sharing between more than 2 tasks which are often specified as being members in a common group or collective. So in this case, we have many tasks that shares the data. So for example, we have 4 tasks, and all the tasks can produce data and send it, and all tasks could receive data from other tasks and consume it. So in this case, this is called collective. And as I say, always it depends on the scenario. It depends on the nature of the application. Nobody can tell you, if let's say you came to me and you ask me, doctor, I'm trying to solve a problem. I design an algorithm, but that algorithm need to be run in parallel, and I have many tasks. Can you tell me how can I run them? Is it what kind of communication I should use? Is it better to use synchronous or asynchronous? I cannot answer you. There is no standard answer for that, guys. Why I cannot answer you? Because I don't understand the nature of the problem. So if you don't explain to me what is exactly the problem, then I will never be able to answer your question. But if you explain to me and I understood how the problem is working by nature, and at that point of time, I can give you a proper answer. Depends on the nature of the application. Okay, guys? So understanding the problem nature is very critical stage or very critical step. Okay. Okay. As we mentioned here, we have point-to-point communication and collective communication. So the collective communications, we have many types of collective communications. So the first type is broadcast. So maybe one task could send the same data to all tasks. So this task here sends the red data to the other 4 tasks here as a broadcast. So every task here has a copy of the same data, right? They all have the red rectangle, right? This is what they call it, broadcast. The other type is called scattering. So the scattering actually is to send one task could send different data to multiple tasks. Okay, so here this task receives the red rectangle, this task receives the yellow, this task receives the blue, or I don't know the exact colors because I am semi-blind of colors, guys, so don't care. I will call it blue or maybe light blue or whatever, and this is maybe orange, or I don't know what color is that. So here, as we can see, we have multiple tasks that receives different data from the same source. Okay, this is what they call it, scattering. So the other type is the opposite way. So many tasks will send different data to the same task. So in this case, different colors are sent by different tasks to the same task here. Okay. Then these two, the first and second, these two are called one-to-many communication. One-to-many communication, and these two are many-to-one. So these two types of communication has no problem with congestion, but this two has to be carefully designed to avoid congestion. Why? Because here the resources of the subtasks could be more than the resource of one task, so this task could be overwhelmed if the other tasks keep sending a lot of data that this task cannot handle. So we have to always keep in mind the congestion in mind, and we have always to avoid it. This other scenario actually, or other type, they call it reduction. So the reduction here, there's some data sent to from different tasks to the same task. So here, this task will keep the summation of the values that's sent from the tasks. So they don't need to keep number 1 here and number 3 here. So they don't need to to keep a track that number 1 is coming from task 1 and number 2 is coming from number 3 is coming from task 3 and so on. They only need to receive the numbers and they combine them in one variable and they keep the total value of that. So this is what they call it, reduction. Okay, factor number 6, efficiency of communications. So very often the programmer will have a choice with regard to factors that can affect communications performance. Only a few are mentioned here. Okay, so the programmer will have a choice with regard of factors that can affect communication performance. So the programmer need to handle all of that stuff and need to be careful what technique they need to use and what kind of communication. Is it one-to-many, many-to-one? Is it scattering or broadcasting? Is it one-to-many or many-to-one? Or what kind? Is it asynchronous or synchronous? Yeah, they have to decide. Depends on the nature, actually, of the problem, as I always say. Which implementation for a given model should be used? So the programmer should decide. Using the message passing model as an example, on MPI implementation may be faster on a given hardware platform than another. So this one actually is another scenario because MPI actually is a library or a platform that's available for us to use. So maybe, for example, we use Windows machine and maybe we have another Linux machine. So maybe we have different implementations for the MPI. So maybe the MPI that's installed on the Windows machine is faster than the one implemented for the Linux machine. So the performance may be different, depends on the implementation of the MPI. So MPI implementations actually we have many types, many versions, many distributions actually of the MPIs from different vendors, and some of them open source, some of them free, some of them are commercial. So we need always to have the right implementation of the MPI that could provide us better performance for our application. Okay. So what type of communication operations should be used? So as I said, this is the responsibility of the programmer. So as mentioned previously, so the programmer should be responsible of the selecting the proper type of communication, whether to use asynchronous or synchronous or one-to-many, many-to-one, or whatever. So asynchronous communication operations can improve overall program performance. So as we said previously, the asynchronization or the synchronous communication is much better than the synchronous. Why? Because asynchronous is non-blocking, so there is no lock and wait for that. So the resources cannot stay waiting for other processes to finish or to send data to let them continue processing. Okay, so while they are waiting for a message from another task, they are still doing another job. That's why the resources will be fully utilized or optimally utilized. But in the case of synchronous, which is considered as a blocking technique, so the resources could be waiting for long until they receive the trigger to continue their processing. So in this case, the resources will not be optimally utilized. So network media here, the programmer also or the platform is very important to decide the network media. So some platforms may offer more than one network for communications, which may offer more than one network for communications, which one is best. So here, for example, as I said, if let's say we have a cluster of computers and the communication is going to use the network, the communication network between the computers, which is, for example, based on fiber, 1 gig fiber, or maybe depends on Cat5 or Cat6 network, which is maybe Ethernet with the speed of 10 megabit per second or 100 or 1 gig or whatever. So that specifications or a media type of the network is going to affect the performance of the network. Other scenarios, if let's say we have a supercomputer that has multiple resources, multiple processors, and very huge amount of memory, so the communication will be done inside the machine itself. So there is no need for the program or the tasks to use the real communication network. Okay, so they will need to use the memory sharing or the internal communication network among the processors and the memory buses. Okay, so this is depends on what resources or what hardware or what type of platforms that we are going to use or we have already using. Okay, some of the platforms provide multiple choices of communication. So, for example, they can communicate through the network and as an option, and also if the network is failed, then they can use memory, for example, memory sharing. So this is another scenario. The question here, which one is better? Actually, we cannot say that the cluster is better than the supercomputers, and also we cannot say the supercomputers are better than the clusters, because it depends on the resources that we have or the budget, and also depends on the nature of the application or the nature of the problem. Okay, guys? So there is no standard answer for this question. Okay. Factor number 7. Overhead and complexity. So complexity is very huge, important, crucial factor. So we have to carefully consider the complexity, and whenever the application is very complicated, we have to carefully design the things and carefully use the resources and carefully use the techniques like synchronous communication, the techniques of look and wait. Also, we have to try to avoid the deadlock, try to keep everything under control. Okay? So the overhead and complexity are very crucial factors. Overhead must be minimized. Complexity also must be minimized, but to some extent, because complexity sometimes cannot be fully avoided because of the nature of the problem. Okay? Last thing here is factor 8. Finally, realize that this is only a partial list of things to consider. Yes, here in the previous slides, we only mentioned and discussed some very common scenarios or very common factors that we have to consider as programmers whenever we try to design a parallel program. Okay, but there are a lot of factors that we cannot discuss here because they are maybe very specific to certain problems, or maybe very rarely happening, something like that. So whenever we start designing a parallel program, we have to carefully understand all directions of the problem. We must understand how the problem works, the nature of the problem, is it parallelizable or not, how much resources we have, what's the cost, how much budget we have, how much time is available for us to achieve the tasks, what's the business requirements, what's the organization requirements, what techniques we need for communication, is it the tasks, is it independent or dependent, if semi-dependent, it requires communication, the communication needs synchronization, so how we synchronize, should we use blocking technique or non-blocking technique? A lot of things in mind. We have to keep them in mind. Okay? How to keep them in mind? Actually, after we understood the entire directions of the problem nature. Okay, so we stop here. for today, and we continue inshallah tomorrow. We stopped here. Okay, so tomorrow we are going to talk about the synchronization, data dependencies, load balance, granularity, and so on. Okay, guys? So I hope that you enjoyed this class. I hope you understand also what I had explaining all the time. And guys, please, honestly, I'm telling you, I'm really waiting for your questions all the time. But unfortunately, sometimes I feel that maybe you are very shy, not asking, or maybe you really understood. So it's if you really understood what I have explained, that's really my pleasure, my really my happiness. Yeah, I hope so, guys. So please, if you have any question, try to use the all communication channels. Try to send on WhatsApp group, or maybe send by email, or even contact me directly. All of you have my number. So please don't waste the opportunity of this course to improve your skills and knowledge about parallel programming. Okay, guys?
Doctor.
Yes.
Excuse me, doctor.
Yes.
It's okay, Shed, go first.
Yes, no problem.
For the exam, until what chapter, Doctor?
Okay, let me stop the record first. Okay, thank you guys, and see you inshallah next week. Assalamu alaikum warahmatullah.